With that, I'd like to introduce the Honorable Dr. Will Roper. We're very, very fortunate to have Will here with us today. Will is currently a distinguished professor at Georgia Tech's School of International Affairs, where he lectures on the intersection of technology and national security. He is a board member and advisor to multiple startup companies and venture capital and private equity firms. Previously, Will served as the Assistant Secretary of the Air Force, responsible for all acquisition, research and development, logistics, really, really important position within the Air Force and Space Force. He oversaw that entire portfolio, $60 billion a year portfolio for the Air Force and Space Force. He is known as being a real innovator within DoD on how to get things done quickly and think outside the box. He was the founding director of the Strategic Capabilities Office within the DoD, which has really driven a lot of how the DoD is innovating and looking at new capabilities and new technology for the warfighter. He is not only broad, but he is technically deep. He is a Rhodes Scholar from Oxford with his doctorate in string theory as well. So we are very, very fortunate to have Will with us here today. So I'll hand it over to Will.
Thanks, Scott. And it's going to be a lot of fun spending time with you all today. And if you have any trouble hearing me, let me know. But I think given this is a new topic where there's a lot to learn from everyone involved with it, I'll give you some opening remarks about where digital transformation and Industry 4.0 is globally. I want to share why it seems to be challenging for organizations to make this pivot, but what the opportunities are and what the future will likely look like on the other side of the next industrial revolution. Now, I'll tell you up front, anytime I talk about this topic, I tend to reference the original Matrix movie. So if you have not seen that movie, I highly recommend it. But there are going to be spoilers in this talk, so you might want to stop your video now, go watch the movie, and then come back and watch this online, because I think it helps. It has helped me talk with former teammates when I was in the Air Force. It helps me talk with industry today as a consultant for McKinsey & Company about why digital transformation is a different thing, even though we've been using computers to do engineering for decades. So let me give you how I got into digital transformation. So I was running the Air Force program portfolio, and we awarded a new airplane contract called the T-7. And the program was significantly cheaper than we had estimated. It was $10 billion cheaper than we had estimated. And we knew that we hadn't made an error in our math and something had to be different. And so we started working with the provider of the capability, in this case, Boeing, to understand what was different about the system. And the difference was that these digital engineering or digital transformation techniques, and I'll define those in a second, were being applied to military aviation for the first time. And they offered this amazing possibility to speed up the program while reducing its costs. And when you've saved $10 billion, say again, Scott, are you having audio issues on that?
I'm muted. Will, I think it's probably somebody else. Lisa, can you see who's talking and mute?
Yeah, this thing you have to be wary of in a large virtual gathering is that you don't become center stage without wanting to be. So anyway, we saved $10 billion. You want to learn more, right? You want to apply the same approach to everything. And so I started digging into what exactly is digital transformation and who's good at it. And I ended up working with McLaren Racing in the United Kingdom that was doing fantastic digital design, digital testing, digital certification. And that's when I got the potential of digital transformation and what it really was, and started talking to my Air Force and Space Force colleagues about it. And my initial feedback from them was, we're already doing this, Will. We've got computers to do requirements. We've got computers to do design, computer-aided design, CAD. We use computers to model performance. We are digitally transformed But I looked at what they were doing compared to what McLaren Racing was doing and said, we're not even in the same universe. How do I get the message through that digital transformation isn't about using computers everywhere? It's about the integration of all of those computers to achieve a level of realism that has not been possible before. And so not knowing another way to communicate, I decided to use the movie The Matrix, which was pretty mind-blowing for its time, continues to be, something people think about and quote today, because it was the first really popular movie that posed the idea that a simulation could be close to reality. In fact, a substitute for it. And I won't try not to spoil the movie for you, but that's the basic thing that gets you thinking about the digital world compared to the physical. So we're not trying to create a science fiction reality around us. That may happen at some point in future, but from an engineering perspective, why haven't we used digital or virtual realities to do engineering before? The Matrix gets you thinking about that. How close can you get a virtual reality to a real one? Well, Formula One arguably is the farthest ahead on answering this question. And their answer is inspiring. The agility that they demonstrate week to week for racing is unlike anything I've seen before. They do not have the hang-up anymore of something being real if it's physical versus not real if it's digital. Their choice of whether something is real or not is based on the level of uncertainty about the thing itself. And if the level of uncertainty is acceptable, even if the thing is entirely digital, it's real for them. They make real world decisions that win or lose races in a way that a team that is only doing things in physical reality could never dream of, which is why the entire sport innovates this way. They started because costs were capped and they had to find a different way to innovate that wasn't expensive, and convince themselves that they could replicate everything about racing, the car, the engine, the rubber literally meeting the road on the tire, that they could model all of that to a level of such precision that the error from the model was within acceptable tolerances for real world certification. And once they were able to do that, to model the racetracks and the environment, they no longer needed to build physical cars. They could innovate digitally. And what they do now is, it's just incredible compared to other industries like aerospace. The average team builds 30,000 digital cars per racing season, about 1,000 for every unique racetrack. They're all looking for small advantages, like fractions of seconds around these tracks. They are being improved and modified all of the time to find the best one for the given race day. When they make that car, they have a near 100% degree of confidence that the car will perform in the real world exactly as it did in their digital model. So much so the drivers can begin training on cars that don't exist yet. And during the race, the physical car is instrumented with hundreds of sensors that stream back hundreds of gigabytes of data that are used to improve the models themselves, and then the cycle repeats. It's so fast and iterative that on average, a part is being redesigned, retested, and recertified every 15 minutes. By the end of the racing season, 85% of the car is different. And the car that finishes the season, if you raced the car that began the season relative to it, the first car would be the last place finisher, not even competitive in the field for the last race. So from this perspective, a racing team doesn't build a race car to win races. They have to have a superior race car building process. It's the process that wins. It just happens to be applied to racing. And for the process to be fast and iterative and affordable, it has to be completely digital. So what I realized from working with Formula One is that this is really, digital transformation is really bringing agile software approaches to hardware. That's it. It's as simple as that. When you look at how Formula One works, the same kind of storyboarding, sprint cycle, deficiency retirement, focusing on velocity of getting out minimum viable products that can be applied in digital racing scenarios that become bigger and bigger products, and then finally the real racing car. It looks like agile software. But we are at the very beginning of building a tech stack that will allow hardware to be built as agilely as software. And that's what's holding back digital transformation. And I'm going to explain why that's hard. You probably already guessed the answer, but it's going to be a lot harder than what has been done in the software world. But we can take inspiration and copy all of the best practices from software development. We don't need to and shouldn't relearn them. But the reason hardware is going to be different is that hardware compiles in the physical world, right? There is physics, and physics gets a vote. And in the past, since the very early days of building physical systems that interact with the universe, we have tried to build models of them to lower the risk of their use. So you can go all the way back to the 1920s or 30s, I believe, for the earliest aircraft simulators, the Link simulators, that saved a lot of lives. There were a lot of crashes for, say, like Army pilots that were delivering mail using aircraft when aircraft were still new. The simulator helped do better training and better avoidance of weather and understanding of turbulence and understanding of the mechanics of flight without having to put people at risk. So simulators are not new. They've been mechanical for many decades, and then now for a few decades, they've been digital. But simulation always was connected to test, at least in my mind. You would design something, then you would simulate it to get a sense of how it's going to work. But you would never go from that simulation and go build it and sell it, or go build it and operate it without prototyping and testing. Prototyping and testing were the rubber meeting the road. You didn't feel you understood what you had designed until that happened. There was a physical step involved because the design doesn't compile until it interacts with physics. It interacts with the universe. And what has happened in Formula One, and is beginning to happen in other industries, is we can represent, for many applications of engineering, we can represent the universe so realistically in a virtualization that we can skip the physical prototyping and physical testing step if we believe that the model has sufficient anchoring and validation. So this idea of a metaverse, which is very focused on like entertainment right now, this idea of a metaverse is already becoming a reality for engineering for many types of systems, where we can create a set of interconnected models that represent the reality of that system, including the physics of it, to such a degree that we no longer need to build the physical system and test it. Now, don't go too far. Like, if you don't understand the physics and you don't have enough data to anchor it, you'll still have to physically test and prototype. But just like Formula One, you should stream that data off, use it to anchor your model, and never recreate that data again. In the world of hardware, we recreate a lot of old data. There's a lot of non-recurring engineering. And in the future, digital transformation offers us the hope of ending non-recurring engineering and only building and testing to collect data of a certain type one time. But it's hard. And I've been helping a lot of companies do this since I left the Air Force. But let me explain first how we applied this in Air Force programs and what was hard about it and what is currently holding back digital transformation in many industries today. So after having that T7 experience, getting to go learn how McLaren did racing, which was just as science fictional as the Matrix movies to me, I came back to the Air Force and said, well, we need to do this. And a leading candidate was the replacement for the Minuteman III intercontinental ballistic missile. This is like $100 billion program. and you can't test it a lot, right? We don't test ICBMs frequently, about 4 times per year. That's not a lot of test data to validate a new system. So we needed something different. This digital technique appeared perfect. So I told our team, we are going to do this. And we hit a technical speed bump, and that in our hardware-rich Air Force, and most industries that build hardware are hardware-rich, which makes them model-rich. Everything they build, there's a model of it. It was built by some subject matter expert for that subject matter expert to use. And you and I cannot easily use it. We need people to use it. These models are not connected to each other. They're connected to people. And for us to be able to digitally design and digitally test and digitally certify something as complicated as an intercontinental ballistic missile, we needed the models to work together as a seamless ecosystem. This is a concept often called a digital thread, that the representations of your model from your system, whether it's the requirement of the system, how it should perform, to the structural design in CAD, to the physical performance in some physical model, even a high performance computational fluid dynamics model, that if that thread is cut at any point, meaning you are not having data shared machine to machine between the models, you are introducing a potential source of error that can invalidate the digital results and force you to do physical testing. A digital thread has no cuts. You can seamlessly move across all different representations of that system. And we built one for the intercontinental ballistic missile replacement. And it took a team of very talented airmen and guardians to build it. In fact, led by 2 PhDs from MIT who happened to be in uniform for the US Air Force, were able to do this. But learning from them, this is not trivial to do, because models and simulations are trying to represent reality, but they're just estimations. Like humanity will never pull together the computational power of the universe. I'm sure someone's estimated what it is, and I'm going to look it up after this talk. But I mean, the exponential would be so high that, I mean, we would feel, we wouldn't even make it on the rounding error for that type of computation. We are taking baby steps into representing, the physical universe around us, and we do that with lots of estimations. We have to know the level of computation, the time step between sequencing. If you're flying in linear flight through laminar conditions in the atmosphere with low turbulence, and the turbulence scale is on a characteristic length that's bigger than the aircraft, you don't need to run a turbulence model that may be modeling at the microsecond level. But for certain areas of flight where you're flying right on the area of the performance envelope where you expect to stall or be unstable, where you have variable conditions in the atmosphere, maybe it's an extreme condition of supersonic flight or hypersonic flight, you likely do need those models. So models make estimations, and they try to use their computation efficiently, because we cannot recreate the universe. And how those estimations are made matter. If you make even one mistake in trying to glue the models together, you can get results that are not just wrong, they're dangerous. And so this is not a trivial thing to do. This is what's making digital transformation hard. It's easy to build something that's near reality. It's hard to build something that you can truly certify is reality up to acceptable error. And so for companies that are trying to do this, and let's consider the Air Force and Space Force companies, there's this upfront challenge that they have to go through, which is gluing their models together so that it becomes a digital thread that has no error sources when translating between different areas of the product's life cycle. But once you've done that, it's magic. It's truly magical on the other side. And just to give you an example from that ICBM program, in the past, we would have been lucky to maybe do, I don't know, 10 very detailed designs of a new system in a military program. You know, maybe a Rockstar team, you do a few more than that. We're able to do 6 billion designs, all high fidelity designs, because we can do everything digitally and not worry about translation error. Can vary parameters and understand the cost impacts, performance impacts, the maintenance impacts, just in the blink of a digital eye, which made us highly confident that we selected the right missile to build. Very similar to how Formula One, after they design 1,000 cars for a racetrack, feels pretty confident they picked the right one when it's time to go physically build it. We have the same confidence. That is a level of digital agility that is just not precedented in traditional hardware building. It looks like agile software. You are not spending your time worrying about the physical integration of things, because that's now de-risked digitally. And since leaving the Air Force, I've been helping companies do this, is figuring out the best way to digitally transform, figure out the most expedient way to glue their models together to create a digital thread so that they can unlock the magic on the other side of it. Now, the magic they're usually initially hoping to unlock, and I'll share the business case, because it matters, right? For things to happen in the world, there has to be an incentive and return on investment for doing them. So it's important for you to understand how companies think about these investments early on. But then I'll finish with what the implication is going to be for the world once this is the norm for how hardware lives and interacts with the world of software, and why it's not going to be good to sit back and let this transformation happen without leading it. You don't want to be behind this power curve. But let's first talk about the economics of it. So when you have something like a digital thread that interconnects all the models, like if you're a CEO of a company, what are the things you care about? Well, certainly lower cost and speed matter, and that may be enough to convince you to do it. But it's important to understand beneath those high-level metrics, what is actually happening on the teams. Well, when models are integrated together and you can put automation in between them, similar to the way a software development tech stack has a high degree of automation that ensures things like security are happening automatically in the background, gives you the ability to do things in parallel. And that's not common in a complicated system that's driven by hardware. You typically have the driving subsystem that completes its design first. It documents what it is in an interface control document, and then other people ensure their subsystems integrate with it. There's a good degree of doing things in serial that cannot be avoided, because integration is risky, has historically been risky. And so engineers spend a lot of their time building a physical system, de-risking the integration of it. In digital transformation, there's almost no risk of integration. The models ensure that systems being designed concurrently can integrate together. So not only does that allow you to do things in parallel, which speeds you up, it actually increases the quality of the engineering time. There's more time for innovation and problem solving than there is in a traditional program where integration ends up hitting the button on the stopwatch and says, pins down, time for good ideas are over. We now need to integrate and go into production. The cycle times is a big deal because it allows risk to be retired when they're small, meaning that the overall risk of the program comes down as it speeds up. Especially if you've got a digital test environment. Imagine being an engineer and you had to wait 5 years to get any data back on your design and that you would consider to be valid data, and now you can get it like the same day that you asked for it. I've seen companies do it within a minute of asking. Who knows? Who knows what will happen when this is being done by algorithms themselves. So the cycle time is not only speeding things up, it's reducing the risk. So look at what we've had already. I'm speeding things up through parallelization. But because I have a high degree of automation between the parallel activities, I'm enriching the time being spent in those parallel blocks of activities, as well as lowering the risk of the things happening in it. I mean, when does that happen? Where you get like win nested within each other for doing this upfront thing. Of course, the fact you're going faster, reduce cost, and there's some other things that are pretty interesting once you've got a physical system that's interacting with its digital one. But that gives you a sense of why CEOs care about this. Most companies, like 90% of companies, say that digital transformation is a top priority. But equal to that 90%, 90% also say they don't think that they are pulling out the value they expected because this is hard to do. And so it really does take the visionaries with the commitment to fund to create these digital threads so that you unlock the magic on the other side of it. The companies that I see doing it are doing it for competitive reasons, they're doing it for financial reasons. But there's another reason that we need to worry about, and I'll end with it, and then I want to take questions from you. So think about what we've just talked about. We're talking about agile software applied to hardware. And now how are we able to do that? Well, we really turned the hardware into the software. We did that via digital design, digital test, right? We created an engineering metaverse so that the hardware could become software in it, and then we just apply agile software processes. Now, that's a cool idea, right? Turning hardware into software. It's a cool idea to think that hardware will now be able to eat the world too. But think about what it also implies. It implies that AI is going to be able to draft along the same path, ride this surfboard to learn how to master the physical world. In fact, I've already seen companies, I've already worked with companies that are doing this. So you think about mastering the physical world, and we're seeing companies try to do this with self-driving vehicles. The general physical world is, it's very chaotic. There are lots of human factors. It's not all physics, and the physics in toto is very complicated. So in order for AI to master physically driven things, it needs a richer data source than physical testing, which is why self-driving vehicle companies have to create very realistic models of driving around in order to create the training data for AI to master the real world. Now, they've come a long way, and it's really the regulatory issues that are making it a challenge to get it fully over the goal line. What doesn't make the paper as much are some other applications that are super interesting, and I think a harbinger of what's to come. The New Zealand America's Cup team, so this is competitive sailing, created a digital thread for sailing. Now, this is a controlled environment like Formula One racing. It's not like self-driving vehicles that are interacting with the world, but they created a virtualization of sailing, the sailboat, the water, the wind, the boat design, the physics of it. So that was so realistic that they could make real world decisions inside of that metaverse. But rather than have humans do it, they trained an artificial intelligence to sail, to design boats. And what was intriguing to see on this team is the AI quickly mastered human sailing and could beat any human team with techniques that humans have been perfecting for centuries. But then it went beyond human techniques, started exploiting characteristics of sailing that have never been available or never fully understood by humans, and developed beyond human expertise in sailing that now humans try to copy and emulate. Very similar to how AlphaGo Zero quickly surpassed human techniques for playing Go and chess. And now the best players in the world try to learn from it. That crossover has happened in the physical world. It didn't get the publicity that chess and Go did, but it tells me that for any system that can be roughly gamified by understanding the physics about it and the rules governing it, that AI is going to be able to master it if you can create a metaverse of sufficient fidelity for the AI to learn as a substitute from learning from physical reality. The sailing AI that New Zealand built didn't know any difference between physical and digital water. It's all the same for them. The race day diagnostics that it collects on from physical water and wind live in the same digital metaverse for it as the digital water and wind it uses to design new boats. The data is consistent, so the outcomes are consistent. And as a harbinger of what this might mean, New Zealand's team won America's Cup last year, aided by this amazing approach to sailing. I don't think this is the last. I think as more and more industries digitally transform, we will find AI applied broadly within those industries. I expect it will quickly master what humans do today and quickly go beyond, and will eventually learn from it. Now, the future on the other side of that could be amazing. It could be a metaverse where innovation happens in the blink of an eye, where all technology moves at digital speeds with very little environmental impact. Or this could be a new means of authoritarian control. So how Industry 4.0 happens matters. And that's why I spend so much time on this, trying to help companies, help governments get their arms around how to do this so that we can make the world on the other side of digital transformation an amazing place, a better place where anything that we think of or dream up can happen at digital speeds. But I'm still learning about this because it's not done yet. The book's still being written. And so I'd like to hear from you. What do you think? Where would you go with it? What do you see as promising? What do you see as risky or a downside? So over to you for questions.
Thanks, Will. That was a great talk. Obviously, very thought provoking. We've got a number of questions in the chat, so I'll try to call through a few of them here at least. Kai Song, did you want to unmute and ask a question?
Yep. Hello. So I was just curious. You talked about like the fast iterative process that Formula One uses for their cars. I was interested to know how like the same amount of efficiency that they get out of those simulations can be applied to things that are not done as often. Let's say like a space mission to the moon or something like that.
It's a great question, Kai. And the way I think about it is that what does Formula One not have to do? They don't have to produce anything at scale, right? So they don't, and they're cost capped, so they're highly incentivized to build as little as they can. So what about industries where either you have to produce things at a large scale, or your example, it's less frequent, like space? So let me address both of those because they're both important. For industries that have to produce things at scale, I think that the gap between research and development and production will shrink. With software-enabled manufacturing, which is, if you've been in if you've ever seen YouTube videos of like an Industry 4.0 factory, there are very few people there. It's mostly automation, software design, software driven, software optimized manufacturing, which is very flexible to bringing new things on. So I think you'll see mass production die. I think that faster cycles where the products continually improve will beat mass production. And because of the high degree of automation and the manufacturing techniques, the economic order quantities of mass production will become lower and lower, and eventually having a more iteratively improving product will be a more advantageous business position than having a cheaper product that doesn't improve as often. So I think that's what will happen in industries that have to produce things at scale. For industries that cannot produce as often, and space is the one we would all think of because of the launch cost, what I think will happen is that the risk of doing new things in space will come down because we can design so many digital satellites before we actually have to build the physical one. Because of those high launch costs, it does create kind of a penalty for taking on too much risk in space, because if you and I design a satellite and we're a little too aggressive in our design, applying like new technologies that we're not sure are space qualified, and we're wrong, then we've wasted our time and we've wasted the launch cost, which is not insignificant. So I think it has put space kind of a step behind in fast adoption because you can't fail forward as easily. I think that digitization is going to allow tons and tons of ideation. I think that creating a metaverse for space is doable because it is a nearly completely physics-driven environment where there are very few human factors. So it should be straightforward to do. The challenge is certification, right? That first time a company or government chooses to let a digital thing substitute for a real thing, that's probably one where you have a deep swallow in your throat, right? Because there's risk associated with that, especially if you're wrong. So the human factors won't be in the modeling. I think they'll be in the adoption for certification purposes. That's a very, very great question.
All right, thank you for answering.
Thanks, Guy. Another really good question by David Bai. If you're there, can you unmute and ask?
Yeah. So I think you did cover this a bit, but I'm assuming that if each of these like different applications has their own specific custom-built simulator, there is a like pretty significant monetary and technological investment in that. So what do you think are the steps needed to like bring this like technology or this application to the general public or commercial applications? Like maybe not Apple or Google, but like a smaller robotics company or a tech startup to like leverage this?
It's a great question. You know, think of, we are all of you, you know, and your careers are about to take off. Think of yourself as being at the stage of the internet from long ago where it was modems dialing directly between computers and you can't search for anything, and you know, it was an obscure landscape that few understood. In the realm of hardware, we are at that step. We have all of these models and simulations around the world. There's one for almost anything that exists physically. Someone built a model of it, but they're all built by people for people. You can't search for them. You can't find them. You can't use them. So I think that what will happen likely over a decade is that the same transition of how to generalize and democratize hardware development will happen for if that happened for software development, will happen for hardware. And when that happens, then similar to like we've seen in the startup boom, it'll be just as easy to create a hardware company as it is to create a software company today. But the reason it's hard is that, you know, these models they're stovepiped, they're air gapped, and even if they were naively connected, like even if we were to just dump them onto like Google's cloud and say, here you go, you probably couldn't use them correctly because there's not that user interface that lets non-experts interface with them. We're at the very, very beginning of writing this new chapter of how technologies can be created. So if this interests you as like as a student, I think this is a fantastic place to really plant your flag in the sand and say, this is the thing I want to make real during my career, because we're at the very beginning of seeing its potential.
Thank you.
Great, thanks. Luca, you had a little bit of a different question about applying ML in this space. Luca Zerga.
Yeah, so I'm just wondering, can these simulations be sped up by using machine learning techniques? Like, for example, I've seen people use ML to speed up like fluid simulation, so you can actually get it at like a reasonable frames per second. But would that work in like these high leverage scenarios? It
does. Yeah, it's a great insight. Formula One does this today to a degree because just to back up a step, the reason the cost caps were put on the sport was that the sport was losing a competitive field. The teams that had the most money were just kind of running away, so costs were capped. Then it spun off all of this digital revolution, and now computation's capped. So you can imagine what that is driving teams to do, is to find clever ways to use computation. And they're doing exactly what you mentioned. They're trying to use machine learning to know how to smartly use their computation so that they can save it for only what matters. So absolutely, I think there's going to be a lot of crossover of artificial intelligence to help do models and simulation better. I think especially where there's a financial benefit from doing it for like a company side of things, or from a fundamental research perspective, where applying that AI allows something that formerly wasn't computationally tractable to become computationally tractable. And I expect that over time, as like more industries create what they may call metaverses, they may not. There's not a a standard term for this, but there'll naturally be research where the boundary of that metaverse is. Like we can represent certain kinds of scenarios, not others. And there'll be researchers at places like MIT who will say, we're going to expand the boundary of what's possible digitally.
Just a quick follow-up. So when using AI in this scenario, would there be any concern about like any additional uncertainties brought into the simulation from that like extra step?
Yeah, there could be, depending on what you're asking the machine learning to do. But if you're if you're asking it to decide, like, let's say you're running a highly computationally intensive fluid dynamics model, and you're using it to determine like which portions of your vehicle, let's say we're doing a Formula One car and we decide we need that high power computation for the airflow under the car for downforce calculations, and say the airflow over the winglets up front and the tail, but maybe not over the center fuselage of the car. As long as that is output and a human subject matter expert can say, I agree, disagree, there is that check and balance, right? The model is still doing what the model is doing. The AI hasn't actually changed the way it's representing physics. It's simply choosing what to abbreviate. So you can still apply a level of human judgment, but it's not going to answer the question whether that abbreviation was good or not, at least not today. But maybe that's the next step, is having AI that plays more of a strategic role in this. But I think the first place we'll see it is just kind of doing what machine learning does well, which is helping make things computationally tractable that the human brain cannot churn through.
Thank you.
Hey, Stephen, Wu, you had a good question about sort of security risks in this area. If you want to unmute and ask it.
Sure. So my question was, what, if any, security risks exist as the general economy moves toward digital transformation, and if digital transformation will result in greater cyber infrastructure vulnerability?
Yeah, it's a great question, and the risks go way up, right? Way up. You've probably heard that famous statement, software has eaten the world. It really didn't, right? It ate the internet, right? It ate the dataverse, where data's created on the internet. It hasn't eaten the universe. The universe has like physical systems in it. It has you and me. Safety decisions rely on things that happen in the universe. The internet right now doesn't have a lot of safety critical things that happen in it. If something goes wrong, there can be financial impacts. There can certainly be logistical impacts that indirectly affect safety and health, like hacking the power grid or something like that. But we're not connected in to physically moving cars and airplanes and industrial equipment the way that we're connected to devices that produce data for transactions and entertainment. This digital transformation is going to change that, right? There will increasingly be a digital representation of physical things. That digital representation will be inside of a representation of the physics in which that physical thing operates. And there will be lots of reasons to have those things cooperate together, just like Formula One does today. Right? Imagine you're driving in your car and a sensor on board finds like a vibration is out of expected tolerance. And you can stream that data off, run a model faster than real time and determine, was this like a 3 or 4 sigma effect? Or is this the beginning of a maintenance issue and you need to take your car in immediately? This kind of stuff I expect will happen commonly. The more this crossover occurs, the more we will rely on the digital representation of the system. It will start being real to us. The realer it becomes, meaning the more real world decisions we make based on it, the more vulnerable the world will be to that digital infrastructure. And just like we're seeing in the internet, where it was created and now we're thinking about privacy, security in a different way, I expect the same thing is going to happen in the world of hardware, and hopefully the world will think about security early enough.
Great. Hey, Will, just one last final question to, and you touched on this a little bit with the sailing example, but do you see a role of creativity here in digital transformation and in digital twins and digital models, or is it really an emphasis on efficiency and doing things quicker?
Well, no, it's going to be the greatest canvas for creatives and engineers in the future, because you no longer are subserving to the needs of the physical world to innovate. The physical world is expensive, right? It's a tyrant to innovation if it's required. It costs a lot to build things and it costs a lot to test things. This is removing the shackles of the physical world and allowing innovators to innovate at digital speeds, whether in software or hardware. I think it's going to open up this amazingly creative time where some of the best designs the world has ever seen are going to be created because they're no longer shackled by real time, and they're no longer shackled by the real world. I think it's going to be an exciting time to be a designer, an exciting time to be an engineer, to be a tester. It's just, I think it's going to feel like, in some ways, going back in time to when things were built faster, but they were riskier. We'll be able to build things faster that are safe. But with that safety, it comes the last question that was asked. There are going to be new kinds of security challenges that we'll have to think about, and the best way to think about them is to begin doing it. Not make them hypothetical problems for a hypothetical future. Let's make them real problems for the real future that is happening today, so that we can get really sharp minds on how to solve them. And if we can solve this, I think we'll find that, like, a lot of things that are impossible become possible. Like a pretty cool example that's not quite here, but is being worked on by John Deere, is completely autonomous farming that's governed entirely by AI, with lots of input from overhead sensors, drones, and leveraging 5G comms to move all of the data around. So, the idea that you could have hardware, the algorithms of machine learning that run on John Deere devices. And if you don't know a lot about farming, it's a highly technical field now that runs a high degree of artificial intelligence, machine learning at the edge on farming equipment. It is no longer like a hardware business. It is a software business where the systems are just, they're platforms and an internet of farming things. It's amazing industry. But they are beginning to push into ever increasing autonomous farming. And my hope is that what we'll find, in like the racing example for New Zealand, will happen in other industries like farming. We'll find new techniques that will produce more food and make the world more sustainable. That AI will be able to explore trade space that's just not accessible to humans, and the world will be a better place. But for every idea that someone poses to make the world a better place, there will be a counter idea that will make the world a more dangerous, a more insular, a more authoritarian place. And so that's why this matters, right? The internet that has happened, like the internet that happened initially, where dial-up computers were connected to each other, is now a footnote in history. It has been replaced by the Internet of Things. It is possible that the Internet of Things as we know it today is a footnote in the future's history, where everything in reality is represented digitally, and AI gets access to it. And you all will say and tell your children and their children that you remember the time when hardware was difficult and challenging and you had to build physical systems to understand how they would work. And that will seem crazy. So getting ready for what we know today to be a footnote in the future's history is the work to do now, to think through this and to make sure that this transformation, this industrial revolution happens for good.
Thanks, Will. It was amazing. Really, really appreciate it. Elisa, I'm gonna turn over to you for the t-shirt presentation.
Great, thanks, Scott. Thanks, Will. We're gonna call up Samantha Hua and Andrew Moses.
Hi, your talk was really exciting, and just thinking about the future of engineering was really cool, especially how like digital threads unlock so many possibilities for us. I learned so much for your talk, and I just wanted to thank you for taking time out of your day to speak with us.
Oh, it's my pleasure. I'll talk about, I'm happy to do another session with you if you want. I love this stuff. I think there's so much to learn here, and I learned from everyone I talked to on it. So if it interests you, the textbook isn't written yet. Need someone to write it.
Yeah, and along with Samantha, I'd like to really thank you for your presentation. I really enjoyed hearing about the importance of, when iterating a product, the difference between doing it physically and digitally and how they interconnect. It's a really amazing addition to the traditional design process. And we'd like to present you with the BWSI t-shirt.
Thanks. I will wear it. We'll wear it in pride. And look, just thank you for your time and your interest. And if there's anything I can do to help you or anyone watching, just be in touch with Scott or with Bob, and I'm happy to go deeper with you.
Thank you so much, Will. We really enjoyed your talk. We're glad you were able to make it today.
My pleasure.
Well, it was great.